Okay, we're going to talk in this section about computing linear maps. And we talked about vector spaces until now. And we have identified vectors with what you usually think of vectors as a column or a row of numbers. So v1 through vn. So this is kind of the standard example of a vector. So let me call this a standard vector. Now, when you're talking about linear maps, there's a similar object that represents the standard linear map, and that's called a matrix. So matrix is an array of numbers. Typically, we'll represent a matrix using letters and then two indices. So this would be the first row, first column entry of the matrix. This would be the first row, nth column entry. This would be the mth row, first column. And this would be the mth row, nth column. So I could say this is a standard representation of a linear map. So just to complete this parallel, this is a standard representation of a vector. Now we know that there are many different types of vectors, but we can always associate it with a representation like this, an n-tuple of numbers, usually arranged in a column. Similarly with linear maps, there are all kinds of examples of linear maps, but the standard representation of a linear map is with a matrix. Okay, and we'll be expanding on this point as we go through the slides. So, representing linear maps with matrices. Okay. So, linear maps are determined by the action on a basis. Now, we certainly have seen that basis is very important in determining vector space behavior, because all vectors can be expressed in terms of a basis. And linear maps behave this way as well. Linear maps' behavior are also determined by how they work on a basis. Okay? We've seen that if we fix a domain space V, a codomain space W, so here's our domain space V and codomain space W. We have drawn many diagrams like this. And suppose we have a basis for the domain, so I often represent basis this way, as a set of linearly independent vectors. So this would be beta 1, beta 2, beta 3. Now, if we have a linear transformation, a linear map, I should say linear map, from V to W, then that linear map H will act on all of the basis vectors. So somewhere in here, I'll have H of B1. I should say H of beta 1. I think you understand what I mean. I'd also have H of beta 2 going somewhere. And finally, I'd have H of beta 3. All right, so like I said, this linear map will act on all of the vectors in V, but in particular, it will act on the three basis vectors. So let's see where we go from here. All right, now suppose I want to find H acting on any possible vector in V. So I'll redraw V here, and I have V here. Now, V can be expressed as a sum of some constant times beta 1, C1 beta 1, plus C2 beta 2, plus C3 beta 3. I won't draw it, but you can imagine you do some combination, go along beta 1 for a certain distance, then you go along beta 2 for a certain distance, then you go along beta 3 for a certain distance, and you obtain V. Now, this vector V is also going to go to a vector in W, so I want H of V, and we will use the linearity property to say, well, okay, if V is some linear combination of the basis vectors, then H of V is the same linear combination of H of the basis vectors. So whatever linear combination I do over here to get V, I'll do the same linear combination over here with h of the basis vectors to get h of v. Okay? So now we're going to systematize these calculations. Here's an example. Let the domain be the polynomials P2, that's the second order polynomials. And we're choosing a particular basis, 1, 1 plus x, 1 plus x squared. It should be pretty clear that that is a basis, that any second order polynomial can be written as a linear combination of these three polynomials. On the other hand, let's the codomain be R2, and we'll choose this basis, 2, 0, and minus 1, 1. And let's suppose we choose a linear map, H, that maps from the second order polynomials to R2, and we specify what H does to each element of the basis. All right, so we say H of 1, 1 is the first basis element, gives me 0, 1. Now notice this is not directly related to any one of these two basis elements, but it is in the span of those two basis elements. H of 1 plus x, which is my second basis element over here, goes to 3, 2, which is also in the span of this basis. And h of 1 plus x squared is minus 2 minus 1, which is also in the span of these two vectors. Okay, so let's see how we can represent this linear map using these two bases. All right. Now, if I want to represent h of b1 in the basis bw, I'm going to have 1/2 1. Why? Let me go back here and copy this. Okay, because I think we're going to need this. Take a snapshot here and copy this. Okay, and then we'll go back here and we'll see if it pastes. Oops, didn't work that time. Let's try again. Sometimes it doesn't work the first time. Copy. Go here. And let's see if we can do paste here. Should be a place to paste. I may have to do it a different way. Let's just do this and see if that works. Nope, doesn't work. All right, let me pause and make the copy and I'll be right back. Okay, so here we go with the copy. Now I want to find the representation using the BW basis for h of beta 1. And it's claimed here that this representation is 1/2 and 1. Why is that? Because h of 1 in the standard basis is 0, 1. But 0, 1 in the BW basis can be written as 1/2 times 2, 0, which is the first basis element, plus 1 times minus 1, 1, which is the second basis element. So this 1/2, 1 gives me the coordinates for h of beta 1 in terms of this basis BW. I can do the same thing for h of beta 2. H of beta 2 was defined to be 3, 2 in the standard basis, but I can express 3, 2 in the standard basis using the BW basis in this way. And the question, you might ask the question, how did he get these numbers 1/2, 1, 5/2, and 2? And you've done problems previously with change of basis, finding the coordinates of a vector in terms of different bases. So you can go back and review that if you don't remember how to do that. Finally, we have the representation of h of beta 3 is minus 3/2 minus 1. Since h of beta 3 was minus 2, 1 in the standard basis, and it's possible to express minus 2, 1 in the standard basis as minus 3/2 times the first basis vector in BW minus 1 times the second basis vector in BW. Okay. So I've explained where we got these numbers here. So we have the representation of h of all of the basis vectors in the domain in terms of the basis vectors in the codomain. All right, now we can summarize the result of this linear transformation by writing these vectors side by side in order to make a matrix. 1/2, 1, 5/2, 2, minus 3/2, 1. Okay, of course the 1/2, 1 comes from up here, and so on. It's not clear at this point why you'd want to write it this way, but you'll see shortly. Now, to an arbitrary domain vector V, which is a linear combination of the domain basis vectors beta 1, beta 2, beta 3, we can apply the equation star, which just gives me the linear transformation of V as a linear combination of basis vectors. So the linear transformation acting on V is going to be the same linear combination acting on the image of the basis vectors. Here, of course, n equals 3 because there are only 3 basis vectors. Right? So C1 stays the same. Now, what's h of beta 1? Well, we computed that on the previous page to be this. You can go back there and see. That was just computed right here. So we're just replacing h of beta 1 with this representation. H of beta 2 with this representation. H of beta 3 with this representation. Okay? So in that way we get h of v as a linear combination of basis vectors. Now we want to group coefficients of like vectors. We'll group all the 2, 0 terms together, and we'll group all the minus 1, 1 terms together. So in the end we have some constant times 2, 0, which is the first basis vector, plus some constant times the second basis vector. Now, if we wanted to write the representation of this vector in terms of the two basis vectors, we want to write the coordinates. So the first coordinate is this, second coordinate is this. All right, so that's the result of the linear transformation in terms of the coordinates relative to the basis BW. Okay. So let's summarize. Equation star, which is that linearity equation, shows that if you want the action of the linear map, which was summarized by this matrix, first what we do is we take any element in the domain and express it in terms of its coordinates relative to the BV basis. If we do that, then the coordinates of h of v relative to the BW basis will be equal to this. Now, just to preview, of course, you can recognize this as the matrix 1/2, 5/2, minus 3/2, 1, 2, minus 1, times C1, C2, C3. Okay? So matrix multiplication naturally gives us the representation of the linear transformation by representing the image of V in terms of its coordinates relative to the original basis. Okay? And so we'll expand on this, but I do want to emphasize that here is the natural definition of matrix multiplication in terms of the linear map that it defines. Okay, matrix representation of a linear map. We're going to generalize this example. Suppose that V and W are vector spaces with dimensions n and m respectively, and I have a basis for V and a basis for W, and I have a linear map that maps from V to W. Now, if you really want to understand this example, this definition, go back to the previous example. We're just generalizing what we did before. Now, if the representation in the codomain basis of the mapping acting on the domain basis is given by this column vector of numbers and the representation in the codomain basis of the linear map operating on the last basis vector in the domain is this column of numbers, then I can represent the linear map with respect to these two bases by the following matrix. Notice that each one of these columns corresponds to a different basis vector in the domain, and it gives the representation in the codomain basis of the image of the corresponding domain vector. Okay, so to understand this, go on back to this example, and you'll see that we're doing exactly the same thing we did up here with this simple 2 by 3 example. Okay. So here it says we often omit the subscript on the matrix because when we're talking about these matrices, usually the two bases are understood. So he means usually you don't include this. All right, let's think of another example. Take the projection from R2 to R2. Geometrically, what this means is if I have a vector in R2, if I take the projection, it's simply going to be the x component, like this. Okay. Now, you're expressing this really in terms of the standard basis. In order to understand what's going on, let's take different bases. So I'm going to take the domain basis as 1, 1, minus 1, 1. In this case, the domain and the codomain are the same. It really doesn't matter to the treatment. You do it the same way. So I have a domain basis and a codomain basis. Now, according to this rule, the domain basis vector 1, 1 maps to 1, 0, right? Because the projection just zeroes out the second component. So from this you can compute that the representation of this vector in terms of this basis is minus 1, 1/2. You can verify that. Minus 1 times the first basis vector plus 1/2 times the second basis vector is equal to 1, 0. Similarly, the projection map pi acting on the second domain basis vector gives me minus 1, 0. Again, the projection just zeroes out the second component according to this rule. So now I want to represent this image vector in terms of the codomain basis. And you can verify that minus 1, 0 is equal to 1 times 0, 1 minus 1/2 times 2, 2. Now, according to the definition we just made, in order to represent the linear transformation pi relative to the domain basis B and codomain basis D, I simply take these two vectors and write them next to each other. Okay, let's do another example. We'll use the very same mapping, but this time we'll use the standard bases for the domain and the codomain. Okay, so we get 1, 0, 0, 1. All right, now the projection acting on the 1, 0 base vector gives me 1, 0. So that gives me a very easy representation of pi of the basis vector beta 1 in terms of this basis. The pi of this basis vector is just the first basis vector in the codomain basis. Similarly, if I take pi on the second basis vector in the domain, that's going to be equal to 0, 0, which is also 0, 0 according to the codomain basis. So if I want to represent this mapping using the domain and codomain bases being the standard basis, I simply take these two vectors and write them next to each other. Right. Another example. Suppose I take the mapping H from R2 to R, defined by this rule, and we'll take the standard basis for the domain and the codomain. Right. So, for instance, this is the first standard basis vector, and that will go to 2 according to this rule, 2 times 1 plus 3 times 0. And here's another domain basis vector. According to this rule, it goes to 2 times 0 plus 3 times 1. Okay. Now let's represent these results according to the codomain basis. All right, the codomain basis is just simply the number 1. So 2 is 2 times 1. So 2 is the representation of H of E1 relative to the codomain basis. Similarly, 3 is the representation of H of 0, 1 relative to the codomain basis. To get the matrix representation, we simply write these two representations next to each other. So this is a 1 by 2. Now notice we went from R2 to R1, and this gave me a 1 by 2. If you look back at the previous maps, they were all 2 by 2, and that gave me 2 by 2 matrices. So as you can see, the dimension of the matrix is related to the dimension of the domain and the codomain. Sorry about that slight interruption. Let's continue. Assume that V and W are vector spaces of dimension n and m respectively. So V has dimension n, W has dimension m. And V has basis B, W has basis D. And H is a linear map from V to W. If H is represented by this matrix here with respect to bases B and D, and V in the domain is represented by this column vector. So in other words, the vector V is equal to C1 beta 1 plus C2 beta 2 dot 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 all the way up to Cn beta n. But if this is the representation of V in the domain basis, then the representation of H of V in the codomain basis will be this column vector, which you can represent, which you can recognize is equal to this matrix times this vector. All right, so that's the basic theorem of this section. Okay, this formalizes the example that began the subsection C, exercise 29. Okay, so we're just saying that you do the same thing we did in the first example. I showed you how the vector that represents H of V was equal to the matrix times the vector that represents V. And you just generalize that using lots of indices. Okay, but the idea should be clear from the example. Okay, so from this we define the matrix vector product. We already know what a matrix vector product is, but this gives us an excuse for a formal definition. You take this matrix times this vector, you do the usual row, column, row, column, row, column multiplication. And that just so happens to give us this linear transformation property. Okay, and you can simply do this multiplication without thinking about bases or linear transformations. All right, now recall that the two matrices minus 1, 1/2, 1 minus 1/2, and 1, 0, 0, 1 were two different matrices associated with the same projection map pi. Okay, let me go back and show you that. Remember, the first time we did it, AB goes to A0. We used these bases, B and D here. The second time we used these bases here and here, 1, 0, 0, 1. Okay, so we actually have two different matrices representing the same linear map. So if we represent this vector v, minus 1, 5, according to this basis, you can work out that you obtain this representation. And the representation of v relative to the standard basis is just itself. If you work out the matrix vector products, you get this result and this result. And this was exactly what we found. Okay. Okay. If we remember this mapping here, AB goes to 2A plus 3B. Here you're just using the fact that the matrix representation works. You can represent H by this matrix here. If I have different domain vector minus 2, 2, and I apply H to it, it turns out that the representation with respect to the standard basis of H of V is equal to 2. Okay, and we'll stop here.